In this video, we are examining what I'm calling the problem of misalignment. So this is in the context of machine learning, and here we're focusing specifically on reinforcement learning, which is quite different than the other kinds of machine learning that we've been looking at. A traditional taxonomy of machine learning is supervised, unsupervised, reinforcement. The difference being simply that supervised learning is when your data is labeled, unsupervised learning is when your data is not labeled. There is a sense where you could kind of fit reinforcement learning into that sort of framework, but really I think it's best to think about reinforcement learning as a different type of machine learning, because it generates its own examples rather than relying on labeled or unlabeled examples. Now, I'm going to talk about in the solution sections, there is actually a technique where you can give it some labeled examples, but that's not essential for reinforcement learning. Okay, so we will use our familiar 6-question framework to examine the problem of misalignment. And I'm going to start out by talking about the elements of reinforcement learning. Okay, so these elements are necessary, meaning you have to have them to have reinforcement learning, and they are sufficient, meaning if you have these 6 elements, that's all you need. There might be other things present, but that's not absolutely necessary for reinforcement learning. Now, the last one, policy, is actually could be unnecessary. I'll talk about that in a second. But yeah, mostly these are the basic conditions for reinforcement learning. Okay, so you have an agent. The agent is the one who makes a decision and takes an action. Okay, then you have the environment in which the agent takes an action. The environment is everything that an agent is able to interact with. We need to talk about the state also. I like the word context. So this is the context that the agent finds itself in within the environment. Then, of course, the action, because the agent has to take an action. The reward, this is important, and this is actually what we're going to focus on in this video. So the reward there has to be a reward structure, and this is going to be numerical, a scalar. It's a scalar reward. So something from the environment rewards the agent, whether that is a positive or negative reward. You can think of it as punishment, but some people in RL just call it a negative reward. That communicates to the agent, that gives the agent feedback about how good or bad the last action was that it took. And so the learning process is about maximizing this. Then lastly, we have the policy. So this is the agent strategy. Now, I said this might not be a necessary condition, because you could just have the agent start out with a complete random policy and it develops its own policy from scratch. Oftentimes, though, the agent, you give it some kind of policy to begin with. Okay, and let's translate those elements into an actual process that we can talk about in 5 steps. So how all those elements work together. So the first stage is the observation stage, where the agent observes the state of the environment. Okay, then the agent has to decide what action to take and takes that action, and that's going to be based on its policy. And as I said, the policy might, if this is its first action, it's possible that the policy is not set, it's just completely random. So that would be the exception. If the policy is random and this is the agent's first step, then that's not going to be true. But for everything else, the agent is going to execute an action based on its policy. Okay, then there is an update to the situation. The environment is now in a new state. And so the agent then gets some kind of reward, positive reward or negative reward, or you can think of this as a reward or punishment for the action that it took. And then the learn phase is the agent updates its policy. Okay, and then the process is iterative until some goal is reached. And here's just a general picture of this, right? So the agent and the environment, the agent has to take an action. Once the agent takes an action, the state updates, and the agent gets a reward based on its action. Okay, so let me give an example of this 5-step process. Let's imagine a food delivery robot. So the observation stage might be that this food delivery robot observes the difference between its current location on a GPS and its destination that it's programmed to find. Okay, so the agent observes that there's a difference. Now the agent, let's imagine for this example that we have told this agent that it wants to get closer to the GPS destination. Okay, so maybe the robot turns right and moves forward. Then there's some update. Now the agent observes that its location on the GPS is closer to the destination, and so the system would then give the food delivery robot, or the algorithm of the food delivery robot more specifically, some kind of scalar reward for being a little bit closer, and now the robot updates its policy. Okay, so this is an overly simplistic example. In fact, if this happened the way that I just described it, this would be a disaster. This would be a business disaster and also an ethical disaster, just because of how simple it was. So, okay, in this example, and it's actually really important about why it was simple, because that's the point of this video. Okay, so the human wants this robot to deliver as fast as possible, right? So I'm going to give the robot rewards for getting closer to the destination. But if that's the only reward I give it, the robot's algorithm is just going to update its policy, that is to say learn, to optimize reaching the destination as quickly and efficiently as possible. Now, that reward structure is incomplete because it gives the robot absolutely no reason to care about courtesy, right? So it doesn't wait for the red light, it just darts right across the street and everybody has to slam on their brakes. It gives the robot no reason to care about physical safety, right? It might mow over somebody's toes because it's quicker to do that, to get to its destination. And it also gives the robot no reason to care about protecting its contents, right? So obviously common sense, we know that the point of getting the food there quickly is so the food intact can be delivered and enjoyed. But the robot has been given no reason to care about that, about protecting the contents. It can jostle it around, anything that gets it there quicker is what it wants to do. Okay, so ethics-aware reinforcement learning asks us to think about what happens before this process that iterates begins, where, among other things, we have to define the reward for the agent. This would be one of those cases where we don't want the agent to just have a random policy. We want to give it a policy and tell it, you're going to be rewarded for this. Okay, so the question of misalignment is, how do we tell that to the agent? So in the telling, there is a possibility for misalignment. Okay, so we humans have certain goals and values, and we're trying to communicate them to the agent. So we want our values to align with the agent's values, and there are some reasons that might not happen, right? So the robot might develop, or the agent, I'll just say agent because the agent doesn't have to be a robot. The agent might develop goals and values that are not our intention. Okay, so let's think about misaligned goals in 3 buckets. So the rewards that we give the agent might be incomplete, they might be incorrect, or they might be exploitable. So all these are examples of misaligned goals. So the agent is simply aiming at a mathematical expression of the goals that we give it, and that may or may not align with our actual goal. So a wrong reward leads to pursuing the wrong goal. An incomplete reward pursues a goal while ignoring other values. The example of our food delivery robot is incomplete, right? So the values of courtesy, physical safety, and protecting the contents, we didn't give it any reason to care about those values, only the value of quickness and efficiency. And An exploitable reward turns the agent into a loophole hunter. So I've given you an example of incomplete reward. Let me give you a quick example of a wrong reward and then an exploitable reward. Okay, so let's imagine that we have a reinforcement learning agent that is a customer support agent. So we give this agent the reward for closing tickets. All right, customers complain or have questions, right? And so once their issues are resolved, then the ticket is closed. But if we told the agent that your goal is to close the ticket, we have told it something incorrect because that's not the actual goal. Closing a ticket is a byproduct of achieving the actual goal. The actual goal is to solve the problem, right? Closing a ticket happens when the problem is solved. But if you would just somehow communicate to the agent, hey, close the ticket, it has no reason to think, oh, I need to solve the problem first. Okay, so the agent, quickly and efficiently pursuing the reward that you gave it, might just like randomly mark things as spam or like give template advice, things that don't actually solve the problem for the customer, and then say, boom, I've achieved my goal, I've closed the ticket. A reward can also be exploitable. This is a real example. This is kind of a famous one in reinforcement learning, like what could go wrong. So there was a design of a boat racing game. And so one thing in reinforcement learning that is sometimes done or often done is you don't just get a reward for the final thing. Sometimes it's better to give like little rewards along the way. So this boat racing game, obviously the big goal is to cross the finish line, but the designers of this game decided to do little checkpoints, right? So it passed this checkpoint, like you can imagine the little flag, little flag stand it goes through, and it gets a little reward for passing that. And then the idea is that it'll want to keep going. Well, this agent was given an exploitable reward, so it figured out that if it crossed this checkpoint and then just spun around, so you can imagine like here's the checkpoint and this boat is just spinning around. So it's racking up points really quickly and efficiently, and so the agent doesn't think of itself as cheating. It's not cheating. It's doing what it's supposed to do, which is maximizing its reward. The failure was on the designer part. We gave it an exploitable reward. Okay, so that was a lot about what is a description of the problem. And let's think about what's familiar about the problem. What's familiar about the problem is training animals. And I mean also human animals. So reinforcement learning is how this is done. Now, this is as old as civilization itself, and for almost all of that, the term reinforcement, that's a new term for a very old concept. But this new term describes that process. So we're going to look at an example from B.F. Skinner, who is known as one of the real founders of behaviorism and designing these experiments. We're going to look at a controlled experiment. This is a real thing that Skinner did, teaching a pigeon to press a button. Now, again, this is a controlled experiment in reinforcement learning, and sometimes we do that with animal training. It'd be really weird, of course, to do that with other humans, but like that process of like strengthening neural pathways by giving rewards is very, very common. But this is an actual controlled experiment that Skinner did. Okay, so let's plug it into our 5-step process. So we have the environment was called a Skinner box. So this is the world that the pigeon had, this Skinner box. I don't know if it was enclosed at the top. I have a feeling it was, but anyways, it was the entire environment for the pigeon. Okay, so there's this environment had a button. Okay, so the pigeon observes all this. What's the pigeon going to do? Well, there's we can think of it. There's three general buckets of actions. The pigeon could do nothing. That's one option. The pigeon could peck the button, or the pigeon could peck at anything else. So let's kind of imagine those are the 3 possibilities. Now let's imagine that, okay, so this is a case where the pigeon does randomly just peck the button. Okay, so there's an update to the environment. The Skinner box registers that peck and dispenses a pellet. The pigeon eats it, so the objective description of that, whatever happens in pigeon brains, there's whatever chemicals are involved, I'm not sure, but subjectively, the pigeon experienced some kind of pleasure, right, from eating this pellet. Okay, so what happened is the neural pathways between pecking and pleasure are strengthened in the pigeon's brain. And if this process iterates a sufficient number of times, then that develops a habit. So at the human level, we call this subconscious decision making. And it turns out that a lot of decisions that we make are actually from habit, right? They occur in a part of our brain that's not the neocortex, not the pink, gray, squishy thing. That's where like logic and our deliberation, when we make decisions like, okay, so what do I want to have for lunch? And you're kind of weighing the options. Here's the pros, here's the cons. That's like deliberative decision making. The vast majority of the decisions that we humans make do not occur there. They occur, below that. We're not even aware that we're doing them. They're from habit. And as far as I know, all of a pigeon's decisions, I don't think they have anything like a neocortex, so I don't think they have any kind of deliberation. So that habit formation is everything. All right, what is new because of scale? So we're going to call animals, and that can include human animals, let's call them biological agents, right? Reinforcement learning has an agent. Let's call those biological agents. And the context that we care about, we're training artificial agents. So this has at least two important implications. One has to do with scale, one has to do with the capabilities of the system. Okay, so when we're training artificial agents, we're not just training individual artificial agents. When the artificial agents have an updated policy, that updated policy can be passed on to an indefinite number of artificial agents, right? Because these are like digital, right? This is an algorithm. So this algorithm is like updated. It can just be like spread as quickly as digital copies can spread. So this is kind of like evolution, but not exactly. I mean, this is like an evolution on steroids. Like biological evolution, this is not at all how it would happen. So, of course, there are adaptations that eventually get selected. We know that. But these kind of learned behaviors, like button pecking, like this pigeon is almost definitely not going to pass on. Its neural pathways aren't going to be strengthened to the point that it has, it passes on the genes that make, its children want to peck buttons. We're training an individual biological agent, and then we have to retrain the next biological agent. That's different than artificial agents, where an updated policy can become every artificial agent's updated policy immediately. A second big difference, and this has really to do with the heart of misalignment. Okay, so when we're using reinforcement learning to train biological agents in a controlled or uncontrolled setting, the reward that we give it is not the agent's whole story. It's not its actual entire reward structure. And that is because evolution has given biological agents lots of other things. You can kind of choose how you describe them: innate drives, instincts, emotional, physiological feedback systems. So the point is that the reward that we give it is not the only, sorry, let me say it this way. With artificial agents, the reward that we give it is its whole world. It is the only reward structure. So the fact that we give a pigeon a pellet or something, that might be in some way incorrect or incomplete or exploitable, but because the pigeon comes programmed with all these other reward structures, the other reward structures can act as a check and balance on a reward that we give it that's incomplete or exploitable or wrong. Okay. Another way to think about this when it comes to human animals, we have common sense. So if I told a human, hey, your goal is to deliver this package as quickly and efficiently as possible. You will get a reward if you do that. The human being would have common sense to be able to know, well, okay, I want to deliver the package as quickly and efficiently as possible, but I don't want to run red lights to do that. I don't want to push other people out of the way to do that, and I don't want to ruin the contents of what I'm delivering to do that, right? You would just know that with common sense. So your common sense sort of fills in the gap. So the fact that I gave it an incomplete reward structure doesn't matter so much. A similar story can be told with closing the tickets, right? So you would understand as a human being, it's like, well, you don't just mean close the tickets, you mean solve the problem first and then close the tickets. That would be completely different than an artificial agent. It doesn't have instincts programmed by evolution. It doesn't have common sense or anything like that. Like what you tell it is what it knows and what it maximizes for. Okay, so which ethical value is relevant here? So here we're talking about the ethical value of happiness. Okay, so what I'm assuming is that there is a desirable outcome that human beings in general can agree upon. And so the misalignment occurs where we're concerned that the agent, the artificial agent, is not going to share those values. And so the alignment is between human values and artificial agent values. Now, of course, humans can disagree about their values, but here I want to focus on the subset of human values that all humans of goodwill can agree upon. I mean, some things like information safety. Now, not literally all humans want information to be safe, right? There's criminals, there's hackers, there's people that are evil, all these sorts of things. I'm not talking about them. I'm talking about things that humans, normal humans of goodwill can agree upon, like we want safety, we want security, that sort of thing. So how can we make sure that the agents have that also? So this is about happiness because I'm talking about an alignment between shared human values and the values of an artificial agent. Okay, so what can we do? There's some best practices here. It's possible to test for bias. Once the policy has been updated a sufficient number of times, you can kind of check to see, how that's all working. There are ways to make sure that an agent's policy is understandable in human terms. You can also do hybrid methods. This is what I was talking about earlier at the beginning of the presentation. Usually reinforcement learning is not located in the supervised, unsupervised realm, but you can give the reinforcement, you can give the artificial agent some labeled data that has been curated that will work to begin its learning. Okay, making sure your rewards have multiple objectives. So yes, efficiency, but we want to check for fairness and safety as well. And human in the loop reward modeling. So this could work for making sure that that human values are aligned. So this would be that when the humans are able to give feedback to say, hey, this was a good action or this was a bad action. That's another way to catch misaligned values. Okay, so those are some thoughts about the problem of misalignment.